The BIBO theorem, bounded input, bounded output. So when we talked about stability before, for example, the Alpenhofer theory, we were looking at the response of the system to an initial condition. So in those cases, we were not assuming any kind of input. Now we're looking at a system that has an input and an output. And we're looking to see if I apply a bounded signal to the input, am I going to get an unbounded output? A signal that blows up, for example. So when we're concerned about stability of systems with inputs and outputs, this is referred to as external stability. And so in order to understand what's going on with this, we need to know properties of signals and norms of them. So if the input is a bounded function, will the output be bounded? That's the concept of BIBO stability. So is it possible then to apply a bounded input to a stable system and get a signal out that is not bounded? And if so, what is the bound we're using? Well, in general, we're going to use a signal norm to bound the signal. It provides an upper bound on the size of the signals. So the concept of BIBO stability is like this. If something like this happens, we have a bounded input signal. So this particular input signal has infinity norm 1. We apply it to our system, and in this case, for a particular system, we could get a response like this. Okay, so the output has infinity norm that's infinite. That is, the signal keeps growing. And so this signal is not BIBO stable. So if we can also talk about the more general concept of input-output stability. We have an input U, we have a system operator S, the output is S operating on U, and we can say that the system is P stable if there exists some constant, finite, non-zero, such that the output in P norm is less than or equal to that constant times the input P norm for all inputs in the space LP, either big LP or little LP. So when we talk about BIBO stability, we're actually referring to P stability for P equals infinity. The limit as P goes to infinity. So that's a special case. Now, in order to talk about BIBO stability, we're going to first talk about something called the impulse response matrix. The LTI system has the impulse response matrix G with elements little g ij of t, which is the response at the ith input when an impulse is applied to the jth input. So gij, okay. And so we have this convolution relationship. So if we assume zero initial condition, the output of the system is given by this convolution relationship. Okay, so G is the impulse response, U is the input that we would apply. The BIBO theorem says that if I have this R by M continuous time LTI system, actually we can use the same theorem for discrete time as well, but S with impulse response matrix G, this system is BIBO stable if and only if we have this condition satisfied. Wow, is that a formula or what? So it's the maximum over I, the sum over j, the integral from minus infinity to infinity of gij of t magnitude dt. If this is finite, then our system is BIBO stable. So this is the main theorem, and we will actually prove this in the proofs video. But this is the basic idea, and this concept then is the concept we're going to look at. Also look at the practice problems to see some examples of these things.